Thank you, Henri. And actually, thank you, Ruth, as well, for emceeing. I'm actually so glad that Ruth is emceeing because imagine if she didn't, then this conference would be ruthless. You have to endure this for the next 30 minutes. Be prepared. Hi, I'm Surma. I want to talk a bit about Polyglot WebAssembly, and that's a word that I made up. Polyglot basically meaning the ability to read, write, or speak a variety of several languages. And WebAssembly really is a pretty good representative of that skill, really. And since you're all here, you are all most likely polyglot because web development alone already involves 3 languages: HTML, JavaScript, and CSS. So welcome, you're a polyglot, and if you're interested in WebAssembly, you might even know one of the WebAssembly languages, so even more languages in your stat, and that's kind of nice. But when I usually talk about WebAssembly, I tend to mention 3 tools of 3 languages that cover very different use cases on the spectrum of WebAssembly. And those are emscripten, which is a tool, a language for C and C++, Rust, and AssemblyScript. So emscripten is a replacement for your good old C or C++ compiler. So if you use GCC or Clang, you will, with an emscripten, use MCC that just compiles your C code or your C++ code to WebAssembly. Then there's Rust, the language Mozilla has been developing and has grown a vibrant ecosystem and community around it. And Rust actually has native support for WebAssembly built into their main compiler, which is great and works really well. And AssemblyScript is something that I'm personally kind of excited about, which is a language that uses the exact same syntax as TypeScript. It's not that you can just take TypeScript and compile it to WebAssembly, but you can write with the skills you already have from TypeScript and write AssemblyScript, and so create WebAssembly through that. So that would allow you to play with WebAssembly without having to learn a new language if you're a web developer. To talk a little bit about the spectrum that I was mentioning of WebAssembly, one thing I look at is like the just works dimension, and emscripten really is the prime example here because they aim to be a drop-in replacement for your old C compilers. Whatever project you have that you might have been writing in C++ or even find a library out there that has been written without WebAssembly in mind, probably even before WebAssembly was a thing, emscripten aims to make that just compile and run it on the web. So they do a lot of heavy lifting and magic under the hood to just bring what is written in a systems language and just run it on the web. Rust is really good here as well. They don't do all this kind of magic straight out of the box, so it is a little bit more likely that code that hasn't been written specifically for the web will not just compile out of the box, and you will need to tweak a little bit, but most of the things can be made to work with WebAssembly and on the web with just a couple of support libraries. AssemblyScript is very different because AssemblyScript is a low-level language. It's really just a very thin layer on top of assembly almost for WebAssembly. And so you have to do a lot of things yourself. And that shouldn't necessarily scare you to take a look at it because it also gives you a lot of control and a lot of understanding of what assembly can and cannot do. So don't let this deter you from looking at AssemblyScript. It's very enjoyable and I would recommend it. Another dimension I want to talk about is the output size because that is something, as we all know, that matters on the web. Like how much bytes does the user have to download to actually start whatever you wrote. And AssemblyScript, as I said, is really good because you are in full control. You write really, really small modules. I mean like on the order of a couple of 100 bytes. Rust, I put it a little bit higher than the Rustaceans will probably agree with. And that's mostly because by default, Rust modules will be quite big, but Rust has the ability to generate just small modules, but that will require you to go and do a lot of like add meticulously crafted code to get to that small file size. So it can do it, but it will just not automatically be that small. And emscripten is the biggest of the 3, mostly the reason that it does all this magic, lots of heavy lifting under the hood. If you use a file system, it will emulate a file system, and that needs code. And I'll talk a little bit more about that later on. And the last thing I want to mention in terms of like the spectrum is the ecosystem around it. And AssemblyScript being, its own language, fairly small team, fairly new. There's not a lot of things there yet, but to be fair, they do a lot with what they have. Again, please take a look at it. I find it very enjoyable. Rust has, grown incredibly in the last year or 2 or 3. and has a huge ecosystem. Actually, I'm impressed with how many things I can find in the Rust ecosystem just thrown at the web. And of course, nobody can compete with the C++ ecosystem. It has been around for I don't know how many decades. It's huge, and most of these things you can use with emscript. And of course, there's more languages that are coming to WebAssembly, because that's what this talk is about, the Polyglot WebAssembly. So I want to give a couple of at least honorable mentions. One of them is Go, that has experimental wasm support, and so you can write Go programs, compile them to WebAssembly, and run them. They're very big currently, mostly the fact that Go is both garbage collected and makes use of coroutines, which WebAssembly doesn't have native support for just yet. So they have to bundle all that runtime code for themselves, meaning it is quite big. But in the future, that will probably go down once these features come to WebAssembly. And the exact same applies to Blazor, which is a project that brings the .NET runtime to WebAssembly. So C# and F# and similar languages, exact same problem. They have their garbage collected, they have coroutines in this case. And currently they are quite big, but still definitely worth looking at and playing around with if you come from a C# background, for example. And the last thing I want to mention here is LLVM, which is not a language, it's a compiler. Like LLVM is the compiler backend project that Clang came from. And it's been around for quite a while, but since version 8, they now have their WebAssembly support in stable. So if you use Clang, you can actually compile C code to WebAssembly just with Clang. And emscript has switched to this new LLVM under the hood. Now, if you use Clang yourself, like manually, you will not have a standard library, which can be both cool and very intimidating. And if you want to know more about this, I wrote an article that you can find here. But basically, you have no malloc. You don't have a sign function. You don't have string length. All of that you would have to write yourself. But it can be quite an interesting experience, but probably not ready for production. And now these number of languages that support WebAssembly will only grow. So for example, what if some idiot went onto NPM and wrote a new compiler for a language called, I can't say it on stage, but it's Brain. So if you don't know Brain, it's a language that looks like this. And of course, that's what you want for your enterprise business engineers to write their code in. It's very enjoyable. Basically, it is a bare bones Turing machine. It's more of an educational device than something you would ever write production code in. But I did it anyway, and so this is actually real. This is a compiler that you can use. You write your code in Brain, and then once you run it through my code, it will generate a proper .wasm file, and it runs. And that is my first compiler, so I'm now a compiler engineer. And that's actually what I want to talk about, because after reading how WebAssembly really works under the hood, I kind of want to see WebAssembly getting used in education. When I was in university, I wanted to write assembler and write my own operating system and like build compilers. And then you try to learn about the processors that you all have in your laptops, and they're bonkers. Like there's no good way to actually understand how they work and know every instruction that they have. So what I've been saying is, don't be afraid to go to webassembly.org and just click that spec button, because the spec is actually kind of well written, and the virtual machine is very well designed, something that actually I was able to understand just by casually reading through the spec. And just to be clear, I'm not saying that every web developer needs to do this. You don't need to do this if you want to make effective use of WebAssembly or be a good web developer. This is just if you're curious, if you're interested. So the spec can look daunting, but mostly because it repeats itself 4 times over, because once for validation, once for execution, the binary format and the text format. But if you want to get started with super low level like handwriting assembly, you only need to look at the text format. And I wrote another blog post on that if you're curious, as a little secondary introduction to how to write text format, which looks like this. And I would almost call it readable. Okay, let's enough of that, go back to polyglotism and languages and all that stuff. I want to talk about Squoosh. Squoosh is an app that we wrote last year. It's an image compressor PWA, so a web app that works offline, has all the good PWA bits, and it makes heavy use of WebAssembly. And this is what it looks like. This point is that you can drop in an image and you can select a couple of different codecs, like a PNG codec and a JPEG codec, and we expose all the options that these codecs have, and you can play around and see how these different changes affect the visual of your image. And we also supply a couple of different scaling algorithms, and all these things run in the browser, 100%. There is no server side, it's all WebAssembly, and all these WebAssembly modules have been implemented with different languages. So all these codecs for images you often find on GitHub or wherever are written in C, because C is somewhat easy to embed in many other runtimes. So all the codecs are C or C++. We actually found a really nice image resizing library in the Rust ecosystem, so that part is from Rust. And we have a piece of AssemblyScript that rotates images. If you're wondering why we have a piece of AssemblyScript just to rotate an image, that will absolutely blow the scope of this talk. So there's another article I wrote where we found out that JavaScript can be fairly unpredictable when it comes to performance. But really the point here is that we have multiple languages working together in the browser via WebAssembly, which I think is kind of cool. So WebAssembly itself only understands numbers. Like you have a couple of different types of numbers, like 32-bit integers, 64-bit integers, a couple of floats. But things like strings or objects, dictionaries, arrays, WebAssembly doesn't know about them. And so what most compilers do is they generate a .wasm file for you, which has the WebAssembly machine code, and then a wrapper in JavaScript. It's called the JavaScript glue code that turns this low-level interface of the WebAssembly module into something that can accept strings and arrays and just makes it a bit nicer to work with. And so one of the first things we noticed when working with WebAssembly is the fact that these pieces of glue code can become quite big. And I say big because I personally have a super low threshold for file size. I know that many people will, ship 500 kilobytes or a megabyte of JavaScript to production and not even flinch. For me, 30 kilobytes already make me feel weird. And that being said, 30 kilobytes is actually kind of fair for what emscripten is doing because it does a lot of heavy lifting under the hood. As an example, emscripten's goal is to be a drop-in replacement for whatever C compiler you have going in your project. The thing is that C is designed or the standard library of C is designed as an abstraction of whatever operating system you're on. And so a high-level function like fputs, which writes a string to a file, has at some point under the hood mapped to something called a syscall, at least on Linux systems. And syscalls are like this weird concept of abstract functions exposed from the kernel of your operating system. And most C API calls will at some level map to one of these syscalls. Now on the web we don't have a kernel, let alone any syscalls, and so what emscripten is really doing is emulating the entire POSIX kernel system interface in JavaScript and mapping it to sensible web APIs if so required. So for example, if you open a file, it will start emulating a file system for you so that your C code can working just fine. If you use OpenGL in your C code, it will start pulling in WebGL and kind of piping those two things together. And of course, that's a lot of code to do all that because there's corner cases and whatnot. And yeah, so the file size will grow over time. And on further inspection, we actually realized, though, that between multiple modules, the glue code is almost the same, barring a couple of constants, a couple of individual functions. And that makes sense because the way you turn a JavaScript string into a C string will most likely stay the same. So I'm working with the emscripten team here, hoping that we can somehow make this more reusable, reshareable, so you don't, because currently the user of Scoosh has to download the same code almost twice or 3 times. And so I'm hoping that we can do better here in the future. But in the long-term future, there's actually an upcoming standard from the WASM team, or from the WASM working group, that I want to talk about for a little bit, and it's called WASI, the WebAssembly System Interface. You can think of WASI kind of like a standardized kernel, almost, for WebAssembly. It's super early, so don't bet your money on this just yet. It's being worked on. It's just a couple of readmes, really. But I think the design is quite exciting, so I want to talk about it a little bit. Currently, WASI is focusing on WASI Core. In the future, there will be more submodules, so you can access crypto devices and USB. For now, it's Core, which is mostly motivated by the use case of running WebAssembly outside the browser on your desktop machines. Because what is currently happening is that WebAssembly was, kind of conceived with the use case of running on the web, but since then, there's more use case of running it embedded in your Android or iOS app, or even standalone on your desktop. So it's now more becoming like a universal binary format, which I think is really exciting. But of course, in that scenario, you need access to files and to, files and to network sockets. And that's really what WASI is providing. So since emscript is already emulating the entire POSIX kernel, I feel like WASI could be a really interesting use case. Now, of course, you're all asking yourself, did I add WASI support to my Brain compiler? And of course, I did. So when you instantiate a WebAssembly module, at least on the web and in Node, you will do something like this. You will use instantiate, and you will pass in the WebAssembly module as the first parameter. Now, the interesting thing is that WebAssembly by default is 100% isolated. It has a chunk of memory, and it can do arithmetic operations on those chunk of memory, and that's it. It doesn't have access to anything, not a single web API. You can only pass in individual web API functions or any API external functions through that imports object in the second parameter. And so by default, the modules that my compiler generates expect two functions, the in function and the out function, because Brain can do input and output, and so it needs a function to somehow communicate with the external world. Now in WASI land, things look a bit different, because now you're basically putting all these individual functions into the namespace that WASI has, WASI core or WASI crypto, and in this case, I'm only allowing the module to read and write from file descriptors. So that's very interesting because it cannot open any files. It still doesn't get access to the file system. It can only read and write file descriptors. And by default, it only has access to standard in and standard out. So in terms of security, this is a really nice model because you have to explicitly give each individual app the permission to use certain APIs on your host system. And now, of course, if you use my compiler and use the WASI flag, you get out a new WebAssembly file, and Wasmer and WasmTime are two of these experimental desktop runtimes that are already implementing WASI to experiment with, and it prints hello world, and so I thought that was kind of cool. I was a little bit proud when that happened. But again, super early, it's mostly readmes and standards work, but there are experimental runtimes which are quite fun to play with. Now to another part is that the tools that WebAssembly has are also polyglot, because they don't really, not even polyglot, it's like they don't even care what language you use, they just care that they can look at the WebAssembly and work on that. So a couple of tools I want to point out is wasm-strip, which looks at the WebAssembly module and strips out everything that is unnecessary, like debug information, unused functions. It basically just makes your module smaller. wasm-validate, which checks that your wasm module is semantically correct. As a compiler engineer, I find that quite helpful. And there's wasm-op, which I want to talk a little bit about, because it mostly just aims to make your WebAssembly module fast and small. So one thing, for example, give me a second. One thing that you should always do pretty much when you run or deploy a WebAssembly module is run wasm-opt, because it will never make a WebAssembly module worse, but it will almost always make it a tiny bit better, and sometimes it can actually turn out to be a lifesaver. So for example, in the case of my wasm module, it made it 30% smaller, which is a little bit unfair because BF wasm is very much explicitly a non-optimizing compiler, but I found that quite interesting in that when I wrote this, I could kind of say, I want to keep my code simple because this was my first compiler, and so I didn't want to make it too messy by making smart optimizations. But also, I knew that wasm-opt existed and that would take care of most of the obvious optimizations for me after the fact. And I think that is actually quite nice. But there is a fun story here from Scrooge, actually. I wanted to ship HQX, which is an image scaling algorithm specifically tailored to pixel art. And I found an implementation in Rust, and so I ported it to WASM, and it worked great. Like immediately, I got better upscaling results, and it looked really good. But what I also noticed is that in Chrome, the CPU got locked in at 200% for like 2 minutes after I loaded the module, which was weird because everything was working. And so it turns out that the WebAssembly that the Rust compiler was generating was like a nasty edge case for the optimizing compiler in V8 for WebAssembly. And so I looked at it a little bit, and the file starts fairly normal, and then these blocks start and they just keep going, and it's a lot of blocks, like 3,700 blocks. I mean, that's a really long blockchain. And so Liftoff, the streaming compiler, actually just looked at it, generated code, and it ran, and that's why the WebAssembly module worked straight up. But then the optimizing compiler was working in the background and just trying for 2 minutes to optimize this mess. And that is not good on a mobile device to just turn in your CPU at 200%. That's not a good idea. So yeah, what we did instead is we figured out that wasm actually can help. So wasm again didn't know it was Rust, just looked at it. It took 20 minutes to actually go through its entire module. But that's build time. Build time is much less expensive than your client's mobile battery time. And so after 20 minutes, we had a module that was about 100K smaller, but also the blockchain was only 700 or 800 blocks long. And so we didn't see the CPU locking anymore on Chrome. And that was kind of cool because, Rust-C didn't generate optimal code in this case, which is fine. And then wasm came along and fixed it without knowing it was Rust. That's cool, I thought. But now one of my most exciting tools that recently have come up is Asynchify. So it was announced a little bit back in the context of emscripten. So I think many people just kind of dismissed it as an emscripten tool, and it's actually a thing that is part of wasm and therefore also language agnostic. So what does it do? So as I said, emscripten will emulate a file system for you. As an example of where I encountered this, so emscripten will emulate a file system for you if you start using file operations in your C code. And it can either store that file system in memory, or it can put it into local storage. And I had a use case where I wanted to store the file system not in local storage, but in IndexedDB. And IndexedDB, as some of you might know, is a promise-based API. And so that means that at some point, a call like fputS, again, would have to map to something that works on IDB, which, is a promise and needed to be awaited. Now, WebAssembly is inherently synchronous and doesn't understand promises, so I didn't want fputS to return before things were actually 100% written or persisted to the database. So I was in trouble here, really, because, there's no wait. And that's exactly what Asynchify solves for you. So you can pause WebAssembly and do asynchronous work and just do stuff, and at some point you can tell WebAssembly, okay, now go back, resume, and execute your JavaScript code. And that's really cool because you make something that is asynchronous look synchronous to WebAssembly. So emscript itself has this really nice abstraction where you can just write some inline JavaScript and you get a wake-up call back that you can call whenever you're ready for WebAssembly to resume, so that's really nice. But again, it is technically language agnostic. So did I add it to my compiler? Yes, I did. So this is a very simple brain. No! Ah, now it's an 18+ talk. All right. So this is a very simple brain talk where we read something from the inputs, we print it back out, and then we do that over and over. It's a read-write loop. Now the thing is with input that if there's nothing available to read from the input, we would have to wait, and wait is inherently asynchronous. So how do we do that on the web? We can now do this because Asynchify. So this is kind of pseudocode. It's a bit more messy in real life, but basically when WebAssembly calls the in function to get the next character from the input stream, I say wait, pause everything, and I will wait for a key press to happen. And once I have a key press, I will resume WebAssembly and return whatever key I have. And so when we look at that, really what I've built here is an utterly unimpressive typewriter. But the potential behind it is kind of cool, because if you think about that, often C APIs are synchronous. So if you want to talk to a USB device in C, those are synchronous APIs. But on the web USB is 100% asynchronous. Almost every call is. So there was no way to plug these two APIs together, and now you can. And that will open up many new doors for WebAssembly to marry to web APIs and make things work on the web that didn't work on the web before. So let's get back first to Squish for a little bit at the end. As I said, we use a bunch of different modules from different languages. Each language may or may not add some glue code that we need to ship, in addition to the app JavaScript code that we already have that orchestrates everything. So really what our app kind of does when you compress an image is this. You have an image as image data, which is just, an array buffer of pixel values. And then you might rotate it with AssemblyScript, you might resize it with some Rust, and then at the end, you run it through a compressor and turn it into a JPEG or a PNG. Now, if you look at this, we don't really have performance problems per se. It's all off main thread, and image compression just takes a bit of time. It's not going to be super snappy fast. But I think we can all agree that this looks a little bit unnecessary. Wouldn't it be cooler if we could do this instead? And that is something that is now being worked on in the WebAssembly working group under the name of interface types. Now this is even earlier than the rest of the stuff I talked about. But the point of this proposal is to bring higher level types to WebAssembly. So as I mentioned before, WebAssembly only does numbers, but with this proposal there's now a way to add support for things like strings or lists or dictionaries or objects, but not necessarily in the way you might be thinking, because WebAssembly will remain to only understand numbers. So a WebAssembly module looks kind of like this. It's a module, it has a couple of exports. These exports are most often just functions, and these functions can only work with numbers, these different types of numbers that WebAssembly has. Now, if your language uses lists or strings or dictionaries, under the hood they have a mechanism to map those to memory addresses and lengths and offsets, to numbers, but that's not really a good user interface to use. So what they have been thinking up is that a module can now bundle a second definition of itself that uses these higher level types. So now we have a function that takes a string and a function that takes an entire JSON object, and then the module will bundle small tiny functions that know how to translate these higher level types to whatever language you were using under the hood and turn those into calls on the low level language. So this way we now have an interface to the module with high level types that we can just use as developers and be very comfortable with that, and then through the translation code block will take care of making it work with whatever the language is expecting to see in the memory. And now that is cool for us as developers, but it also means that now multiple modules can use these higher level types to communicate, because a C string will be different from a Go string and will be different from a C# string, but now they just have this abstract concept of a string and can use it to invoke each other's functions, which I think is going to be very interesting. Of course, there's more future stuff coming along, like SIMD is being worked on, threads are already in Chrome and soon in Firefox, I hope. There's tail calls as a proposal, so that means we're now kind of entering the world where some browsers have support for features and others not yet, and for that reason, if you want to experiment with that, I wrote a small library called wasm feature detect, which does exactly what it says, that it tells you if a browser has support for a certain feature or if it doesn't. So if you're excited about this or if it tickles your interest, try it out. Just go to website.org or hit me up on Twitter or find me outside. I would love to just hear what your ideas are. And with that, thank you for your attention.